Hello and welcome to today's tutorial. So we are going to be solving problems on error. Error is one of the simplest analysis in mathematical methods. I'm saying it from a perspective of someone who understands it very well. I'm sure there will be tons of you out there who do not yet understand it, but I promise after you go through this video series you are going to understand error just like I do, and even much more than I do. Now let's compute the answer for this first problem. We are given a number x equal to 47.36235, and it is rounded off to 4 significant figures. So we want to compute the absolute error, relative error, and percentage error associated with rounding off this number to 4 significant figures. So in problem 1, okay, we are given x as 47.36235. now x is rounded off to 4 significant figures, so x asterisk, which is the rounded off version of x, 4 significant figures 1 2 3 4. So since these digits following is not up to 5, we can just dissolve every other thing and we'll have 47.36. so this is the rounded off version. Now I want to calculate the absolute error, relative error, and percentage error. So solution. So this is our 4SF. So one thing that you notice about significant figures is kind of like they are kind of related sometimes. Significant figures and decimal places are some sort of related. Like in this case, 4 significant figures is corresponding to 2 decimal places for this number. So 4SF corresponds to 2 decimal places. Is that okay? So but that's not our most important thing. Now we want to first of all start with absolute error, so ABSERR. So to calculate the absolute error, my absolute error, which is delta x, is taken as the magnitude of the approximated value minus what, the true value. And it's still the same thing as you saying true value minus approximated value. Well, I'm going to maintain this syntax, approximated minus true value, for subsequent solvings. So this is 47.36 minus 47.36 to 35. Or if we evaluate this, we're going to get a negative 0.00235, and the absolute value of negative 0.00235 is going to be still what, definitely 0.00235. Is that okay? So this is our absolute error, and in the second part we want to solve relative error. So relative error in this case is absolute error divided by true value. So absolute error being 0.00235 divided by true value being 47.36235. So let's calculate with the aid of a calculator. So we got 0.00235 divided by 47.36235. This gives me a 4.961747 times 10 to the power of minus 5. 4.961747 times 10 to the power of minus 5. So this is the relative error. Remember, relative error is dimensionless, it does not have any units. Okay, so let's calculate the percentage error. So percentage error is taken as 100 multiplied by relative error, okay, which is 100 multiplied by delta x over x, which is 100 multiplied by 4.961747 times 10 to the power of minus 5. and this is a 4.961747 times 10 to the minus 3, and if you evaluate it, you get 0.004961747. okay, so this is what you see. Now if you check your options, you might see something like 0.005. okay, that also may work, but for the sake of precision and accuracy, I'm going to leave my answer like this. okay, so this is how we do with absolute error, relative error, and percentage error. Absolute error is the difference between the measure of deviation between the true value and the approximated value. Relative error is the percentage, okay, or the relative error is trying to tell me the fraction of error occupied in a particular true value. The fraction and error occupies in a particular true value. Then percentage error gives us a pictorial representation of the error involved in a system. Like in this case now, we have that the error is around roughly about 0.005%, which is very small compared to the true value. So the error can be even negligible in this case, but I might not really dive into more details on such analysis. So this is just about absolute error, relative error, and percentage error. So let's go to another question. So we are looking at two numbers, x1 and x2, and when we round them up to 4 decimal places, we have 27.0510 and 8.1432 respectively. Calculate the approximation to x1 plus x2 and find the error involved. Okay, so this concept is under propagation of error, and precisely propagation of error through addition. So let's take it step by step and understand how to solve it. So number 2, so you're giving x1 and x2 such that when rounded to 4 decimal places, we get x1 has this property, and let me use a small letter x1. So x1 has this property of, being equal to 27.0510, and x2, when it was rounded, has a property of 8.1432. So they now want me to calculate an approximation to x1 plus x2. Now notice the mixture of my letters. So for exact values, we normally want to use capital letters, okay. Then for approximated values, we may want to use capital letters with a star, or may use the small letter equivalent. Is that okay? So if they want me to find the approximation, how do they put it? Approximation to x1 plus x2, okay, and the error involved. Simply, I'll just assume that the outcome of x1 plus x2 theoretically is a capital letter Z. So capital letter Z is the outcome of x1 plus x2. Okay, so I'm going to now express all of these in error formats. So expressing them in their corresponding error formats, Z can be expressed as Z plus or minus absolute value in Z, and this is going to be what? X1 is x1 plus or minus absolute value in x1, and plus x2 plus or minus absolute value in what? X2. Okay, so I hope this is now familiar to us in propagation of errors. Every number, every true value can be expressed in terms of an approximated value and a particular error, or a measured value and a particular error. Okay, so an approximated value could also be called a measured value. Okay, so my z plus or minus delta z, I wrote delta x here, it's supposed to be delta z, sorry about that. So delta z, so z plus or minus delta z, according to the formula for addition, to be x1 plus x2, then plus minus modulus x1 plus absolute value of x2. So this is how errors propagate under addition. Under addition, the magnitudes of or the measured values will add up, that's x1 and x2, then their approximations or absolute error will also add up. So given that x1 is 27.05 and x2 is 27.0510 for x1, then x2 is 8.1432. So we now have a plus or minus. What are the absolute errors for x1 and the absolute errors for x2? So I don't know. I don't know. So this is where your knowledge of what we treated in the first series, the first video on this series, comes into play. Now whenever you're not giving the absolute error to a particular quantity, you use the maximum possible absolute error. We call it the greatest possible error or greatest positive error, and the greatest positive error is usually gotten by this expression. For instance, x1 is going to be less than or equal to that. The greatest positive error is 0.5 times 10 to the power of number of decimal places to which capital X1 was rounded off to. So capital X1 was rounded off to 4 decimal places. So the greatest positive error for X1 is 0.5 times 10 to the minus 4. The same thing applies for X2. Okay, less than or equal to 0.5 times 10 to the power of what? Negative 4. So this is a standard greatest positive error or greatest ABS max. That's the maximum absolute error, is always less than or equal to 1/2, which is 0.5 times 10 to the power of minus k, where k is the number of decimal places to which we round a number of 2. So anytime you're not giving absolute value, just look at the measured value you're giving, then count the number of decimal places that it has currently, then that's what you now put into this value, and 0.5 will be the scientific part over here, like this. So now that we've gotten our value, my z plus or minus delta z is, when you add this value to this value, let's see what we are going to get. So 14 plus 5 is 19, and 32 plus 10 is 42. So 27 plus 8 is 35.1942, like this. I hope I got it. Then plus or minus, so for delta x1 I have 0.5 times 10 to the power of minus 4 plus delta x2 is 0.5 times 10 to the power of minus 4. So if we simplify, we're going to have a 35 point what? 35.1942 plus or minus this, and this gives me a 1 times 10 to the power of minus 4. Okay, definitely this is a 35.1942 plus or minus 0.0001. So this is my z plus or minus delta z. Okay, so I'll convert this to a tolerance interval. Z plus or minus delta z are all values that satisfy 35.1942 minus 0.001 on the lower limit, then 35.1942 plus 0.001 on the upper limit. This is a 35.1941 to 35.1943. So this is the tolerance interval for the results, capital letter Z. So the capital letter Z is the tolerance interval. So the measured value for the output, which is small letter z, is going to be 35.1942. okay, then the tolerance or the error involved, sorry, is 0.0001. okay, and we got that by assuming the greatest possible absolute error, since we are not giving the absolute error values. And how do we get it? Anytime you're giving a number of decimal places to which you round a number to, you can easily derive the greatest possible absolute error that is involved, then use it in your calculation to get your values. So we are going to move forward to another problem. I hope you understood this one. If there is any thing that is not clear, just leave question, comment, and I will attend to you as quick as possible. Okay, like, share, subscribe, share to your friends and to your colleagues as you watch too. So let's go to another problem. Problem 3. So calculate the relative error in computing x plus y for x equal to 15.20 and y equal to 7.50. Giving the absolute errors, delta x is 0.005 and delta y is 0.001. I wish they would give me 0.007. James 1. Okay, let me not be distracted so much. Let's move forward with this example. So you can pause the video and try to solve it by yourself. So I'm going to solve it, so I hope perhaps you actually pause the video. So let's see if you got the answer. Now we're given, for problem 3, we're giving find x plus y, right? So for we have x equal to 15.20, y equal to 7.50. So they want me to find x plus y. This is x and this is the associated absolute error in x, 0.005. Then associated absolute error in y is 0.001. And they want me to find the relative error in computing this. So to find relative error, ER, okay, to find relative error, ER, like this. So this is epsilon r. This is one way of expressing relative error. Okay, well, let's move forward. 1 2 3 4 5 6 7. Now, of course, we already know that my z plus or minus delta z is what? Of course, x plus or minus delta x plus y plus or minus delta y, and this is x plus y plus or minus delta x plus delta y. We actually derived this in a previous video, so if you don't know how we got the propagation of errors under addition, you should look up that video and try to get the answer. Plus or minus delta z is x plus y becomes 15.20 plus 7.50. So when we add up the errors, absolute errors, we'll have 0.005 plus 0.001. So this gives me a 22.70, okay, 22.7 plus or minus 0.006. Now this is the distribution of error in the result. Now if you want to find the relative error, let me just solve it over here. The kind of relative error that you can calculate from this kind of distribution is called precision relative error. So if they just give you a quantity like this, a quantity, a measured value, and an absolute error, and they ask you to find the relative error, you have to just take the ratio of the absolute error divided by the measured value, which is 22.70. Okay, with the aid of our calculator, we'll see what this gives us. So we have 0.006 divided by 22.7. So 0.00026431718. So my relative error is 0.00026431718, something like this. So this is our relative error, okay, and this is the answer. So I hope you understood and I hope you got it. So I'm going to move to another question. If 11 is an approximation to 10.9, determine the absolute error and relative error. So you should pause the video and try to solve this one by yourself. Okay, let's go. Okay, welcome back. I assume you paused the video and you got answers. So let's verify your answers right away. So I can just assume a random true letter, a random letter to represent the true value. Okay, so P, I love P and I'll not tell you why I love P, but some of you can already guess. So P is for the true value. Okay, now if 11 is an approximation to 10 points, now take note of the semantics of this particular sentence, so that you're not going to get a wrong result. So in this case, my true value, which is P, is 10.9, and the approximation, which is P asterisk, is 11, because P, this is the approximated value. Is that okay? So let's take note of that. My P is 10.9 and my approximated value is 11. So they want me to find one absolute error and number 2 relative error. So quickly, the first case, absolute error. Absolute error is, of course, the magnitude of difference between the approximation and the true value, which is in this case 11 minus 10.9, which in this case, what is 11 minus 10.9? Looks like 100. It looks like what? Yeah, definitely. If you said is it 0.1? Yeah, it's gonna be 0.1. I think my head is hot. 11 minus 10.9. Let's see. Okay, 0.1. So modulus of 0.1, which is, this is delta P as absolute error. This is 0.1. Is that okay? So this is for absolute error, and for relative error. Now, relative error is what? How can we define relative error? Good. Relative error is the ratio of the modulus of the difference between the approximation and true value divided by the true value itself. This is just absolute error all over true value. Okay, so this is where we substitute 0.1. and what's the true value? 11 or 10.9? Definitely 10.9, not 11. So if you used 11, you didn't get it well. So let's find the relative error. We have 0.1 divided by 10.9, 0.009174, 31193. Okay, so this is my relative error, E sub r. Okay, so this is the relative error epsilon subscript r, or delta P over P. Now this kind of relative error is called accuracy relative error. Okay, so there is accuracy relative error where you have to get by subtracting the true value from the approximated value, taking the absolute the modulus, then dividing by the true value. That's accuracy relative value. And the one that I introduced you to previously is when you're given a quantity like this, or let me use z plus or minus delta z, and you ask you to find the relative error. This is called precision relative error. You just need to divide z by z itself and you get precision relative error. Is that okay? So we are going to be working most of the times with precision relative error. So you should be very, very conversant with how to get the precision relative error from a value like this, an approximation value given to you like this. So let's go to another question. So we now have error mixture problems, addition and subtraction. So we want to study about mixture problems now. So these mixture problems will drive home the point, the things that we learned in theoretical backgrounds when I was laying backgrounds in the previous video. So how do I solve mixture problems dealing with addition and subtraction? For instance, if 2.348, 1.369 and 5.101 are u, v and w, rounded off to 3 decimal places respectively, and find the approximation to u minus v plus w. So let's go ahead and figure out the solution to this. So we have mixture problems. So what did you notice when we're solving mixture problems? So under the constraints of addition and subtraction, so there are two things involved. So the measured value add or subtract, okay, or both. Then the second thing is always constant, the absolute error adds up all the time. Whether you're dealing with addition or subtraction, it adds up. So I think I laid the background for this in the last video, where we have for z plus or minus delta z is equal to x plus or minus delta x, okay, plus y plus or minus delta y. That means if I have a value x with its absolute error and a value y with its absolute error, if I add two of them, I'll have x plus y. The measured values add, then plus or minus delta x plus delta y. Is that okay? So this is the case for addition. The absolute errors always adds. Now if I have the same case for subtraction, this is a, then this is s for subtraction, a for addition. So let me assume my result is z plus delta z, and it's actually the subtraction of, sorry, instead of plus I have minus, y plus or minus delta y. So the result will be x minus y. The measured values will be subtracted from each other. Then what will happen to the absolute error? Some people will say they will subtract, but no, they actually add. Okay, so this is not like the normal mathematics, normal sign convention. If you want to understand it, please watch one of the videos I released on this series, and there I introduced a new theory, which is kind of, I think it's a novel theory, although it's obvious, but I think you will find it very useful in understanding the proof of why this equation translates to this equation. Okay, but for now, when you're subtracting, the magnitude or the measured values subtract, then the absolute values add as well. So the same thing will happen when you have a mixture. When you have a mixture of, for instance, z plus or minus delta z, and you have three quantities, u plus or minus delta u, let me say minus v plus or minus delta v, then plus w plus or minus delta w, and minus x plus or minus delta x. So how are we going to resolve this? So it's simple, it's mixed, right? So we're just going to u minus v plus w minus x, then plus or minus, everything adds up, delta u plus delta v plus delta w plus delta x. So this is how errors are propagated under addition and subtraction. The absolute errors always adds up together, then the normal measured values will now follow the normal convention of evaluating the question that was given to you. So we are going to apply this to this problem that was given to us. So I have u given, I have three quantities, u, v, and w. So they are small versions, which is their approximations. And what did they say? Sorry, approximated to 3 decimal place. Okay, 3 decimal places. So this is already giving me an idea of what the absolute error will be. Absolute error, greatest possible absolute error, is going to be less than or equal to what? 0.5 times 10 to the power of minus 3, because that's the standard that was given to us. The greatest possible absolute error depends on the number of decimal place, which you round up in number, and three of them, each of them, they are rounded off to 3 decimal places. This 0.5 is constant all through. Sometimes it's 1 over 2 times 10 to the power of minus 3. So just get used to either using 0.5 or 1 over 2. Me, I love 0.5 very well. So the rounded up version of u, v, and w, I'm going to have a small letter u, which is 2.348, a small letter v, which is 1.369, and a small letter w, which is 5.101. So I want to find the error in approximating u plus v plus w. Now, since they were rounded off to 3 decimal places, okay, of course I can generate my delta u immediately. It's going to be 0.5 times, it's going to be less than or equal to, okay, less or equal to 10 to the power of minus 3. The same thing will happen to v, is going to be less than or equal to 0.5 times 10 to the power of minus 3. The same thing will happen to w, less than or equal to 0.5 times 10 to the power of minus 3. So if we evaluate it, what we are going to get is u plus or minus delta u. Oh, I made a mistake here, right? So let me just, it's supposed to be a minus, u minus v plus w. So u minus v plus or minus delta v, and plus w plus or minus delta w. So what we are seeing is that we'll have u minus v plus w, then plus or minus, then the addition of the 3 what? Absolute errors. So irrespective of whether we have plus or minus, the addition of the absolute value stands. So u is 2.348 minus v is 1.369 plus w is 5.101, and plus or minus. So since 3 of them are actually 0.5, someone can say 3 times 0.5 times 10 to the power of 3. Someone that wants to waste space like me will just go ahead and add 3 of them plus, sorry, so let's simplify. 2.348 minus 1.369 plus 5.101. okay, I need help, calculator. So 2.348 minus 1.369 plus 5.101. Thank God for machines called calculators. We have 6.08. So we have 6.08 times, sorry, plus or minus. So this is going to give me 1.5 times 10 to the power of minus 3. Okay, so at the end of the day, I have 6.08 plus or minus 1.5 times 10 to the power of minus 3, and this is still the same thing as 6.08 plus or minus 0.0015. okay, so this produces a tolerance interval corresponding to 6.08 minus. You can actually stop here depending on what options you need to select, or if the option is expressed in terms of tolerance interval, please quickly spread this to the tolerance interval, and you now have 6.08 plus 0.0015. So 6.08 plus 0.0015 minus 0.0015, just like asking me 800 minus 15, that's 6.0785, and I have 800 plus 15 is 6.0815. So basically this is the answer for u plus v, u minus v plus w. Is that okay? So I hope you understood it. So this is about propagation of mixed errors. So please, I was using my head to calculate. Please try to verify the answers. I hope there are no mistakes, but if there are, at least you understand the underlying concept. Okay, that's the most important thing. But accuracy is also critical. So let's go on and solve one more problem. I'll call it a day on errors. So this one is looking intimidating. We have multiplication and division. So we have the numbers u, v, and w were corrected to 3 decimal places. So correcting to 3 decimal places already gives me delta u to be less than 0.5 times 10 to the power of minus 3, delta v to be less than or equal to 0.5 times 10 to the power of minus 3, and delta w to be less or equal to 0.5 times 10 to the power of minus 3. So I want to evaluate the approximation to u times v over w, then 1 over uv. So let's go about this and see what we get. Oh, uv, familiar, ultraviolet. Alright, don't mind me. So giving u, so this is actually supposed to be capital U, V, and W. Don't mind the people that set the question, don't mind me. So capital U, capital V, and capital W. So when you round them up, you now have small u to be 3.802, small v is 0.795, and small w is 2.508. Okay, so I'm just going to do some recapping for us here. I can actually create a straight line. So what am I doing? So they want me to find a u, v over w, and b 1 over uv, the errors associated with this approximation. So evaluate the approximations. So when you are asked to evaluate the approximations, you need to calculate the value, that's the answer. Then you need to calculate absolute error, you need to calculate relative error. So this kind of like a way to evaluate, since you were not specifically asked for anything to evaluate. So let's see what we get from this. Now, just to recap on propagation of errors with division and multiplication, assuming my z plus or minus delta z is equal to, when I divide a quantity x with its error by a quantity y with its error. So what I'm going to get as my z, I'm going to get x over y plus or minus some absolute error. Now I cannot get this absolute error unless I say relative error first of all. Okay, I need to calculate the relative error, and the relative error has been defined to us as the precision relative error. Now if you follow the video I created, you discover that the relative error for multiplication is the summation of the individual relative errors of the quantities involved. Okay, so relative error in x, which is delta x over x, plus relative error in y, which is delta y over y. So this is it. So now after you've gotten this relative error, absolute error is going to be equal to the magnitude of the relative error times this quantity over here, x over y. Is that okay? So of course absolute error is the product of relative error and the original or measured value. So relative error times this x over y is measured value. And remember, it's actually housed in an absolute sign symbol over here. So the same thing applied to multiplication. In multiplication, we have z plus or minus delta z is x plus or minus delta x times y plus or minus delta y. So what happens? Z plus minus delta z, okay, becomes what? Xy plus or minus some absolute error. Now, the relative error in multiplication is exactly the same as the relative error in division, and I proved it in that video. Relative error in multiplication is the sum of the relative errors of the quantities involved. So anytime you're given any multiplication meaning or division meaning whatsoever, just sum the relative errors of the individual quantities involved. Okay, that will give you relative errors. So this is y over y. Then you can now get your absolute error by taking the modulus of relative error multiplied by the measured value, which in this case is xy. Okay, so this will give you your absolute error. So let's apply it to these two guys over here, solution, and see what we're going to obtain. So remember that we are rounded to 3 decimal place. So after rounding capital U, V and W to 3 decimal place, we got small u, small v and small w. Now their associated errors, delta u is less than or equal to 0.5 times 10 to the power of minus 3. So delta v is less than or equal to 0.5 times 10 to the power of minus 3, and delta w is less than or equal to 0.5 times 10 to the power of minus 3. Is that okay? Now let's see what we get with this. Let's see what we get from this. Now to evaluate a, which is uv over w, so what will our z plus or minus delta z be in this case? So it's just simple. First of all, my value of z is just going to correspond to u v over w. Is that okay? Then my relative error in z will now be, as we said, as far as these three quantities are related by multiplication and division, we're just going to add up their individual relative errors. Okay, plus v over v plus delta w over w. So the relative errors is going to add up, okay, irrespective. So this uv over w is actually going to be, this is I'll be 3.08 3.802 times v is 0.795 over w is 2.508. So this is going to be equal to, let's use the calculator. I'm going to toggle my 3.802 times 0.795 divided by 2.508. So I have 1.205179. Let me just leave it there. 1.205179. Okay, let me leave it there. I just truncated it there. So let's calculate our relative error. Relative error is 0.5, okay, times 10 to the power of minus 3, okay, divided by u. So my u quantity is what? 3.802, okay, then plus I have 0.5 times 10 raised to the power of minus 3 divided by, you have 0.795 for V, and finally 0.5 times 10 to the power of minus 3, that's the absolute error in W, divided by W itself is 2.508. So if we solve this one, delta Z over Z is less than or equal to, I'm just going to factor out that 0.5, so it's going to give me okay, 1 divided by 3.802 plus 1 divided by 0.795 plus 1 divided by 2.508. Everything is multiplied by 0.5 times 10 to the power of 3 minus 3 rather. So let's try to implement this with our calculator directly. So I have times 0.5 times 10 to the power of minus 3. So I have ratios over here. I have 1 over 3.802 plus another ratio 1 over 0.795 plus another ratio 1 over 2.508. So this is a 0.0009598. Delta Z over Z is less or equal to 0.0009598. So please, you need to verify these values by yourself when you're calculating, because I might not be 100% sure of them. But what I'm interested in is that you get the concept, the underlying concept. Okay, that is the most important thing to me. Get the underlying concept and we'll be alright. So let's keep moving. Absolute error now is the magnitude of the relative error multiplied by Z itself. Okay, and this is our value for Z. So this is what we got. So 1.205179. So we have 0.009589 times 1.205179. So we have 0.000 3 zeros actually 9598. I wrote 899598 times 1.205179. So this is roughly 0.0011567. So absolute error, so delta Z, that's 0.0015673. So you can actually evaluate your results, Z plus or minus delta Z, to create the tolerance interval. So Z is 1.205179, 1.205179 plus or minus 0.0015673. Is that okay? So we're going to evaluate another value. Okay guys, where we are going to solve the second part, which is 1 over uv. So 1 over uv is going to be assumed to correspond to z plus or minus delta z. In this case, our z is just 1 over uv, and my delta z is going to be absolute error. Sorry, delta z, which is absolute error, is relative error times the value of z, which is let me say 1 over uv. And remember to place this in absolute value symbol. Now let's first of all start with evaluating z. So z is 1 over uv. 1 over uv, u is corresponding to 3.802 times v is corresponding to 0.795. So if you evaluate this, let's use the calculator to help us. We're going to take 1 divided by 3.802 times 0.795. Okay, 0.3308, 0.330842, 0.330842. Okay, I just truncated it because decimal points were long. Then I want to calculate my absolute error, but I need relative error first. Delta z over z is less or equal to what? So in this case, I just have two of the quantities interacting in this formula, so I'll just sum their relative errors. So I don't need to take any reciprocal whatsoever. It's just going to be the normal way, which is delta u over u plus delta v over v. Okay, it always works like this. So as many quantities as you see in the expression, that's as many relative errors, individual relative errors, that you sum. So delta z over z is less or equal to delta u over u, which is of course, since we are rounding up to 3 decimal places, we have 0.5 times 10 to the power of minus 3 over u being 3.802, and plus we have 0.5 times 10 to the power of minus 3 over v being 0.795. So this is a 1 divided by 3.802 plus 1 divided by 0.795, then all into 0.5 times 10 to the power of negative 3. So we just factored out. Is that okay? So let's calculate delta z over z, and it's actually less or equal to what? So I need bracket, so times 0.5 times 10 to the power of negative 3. So we have 1 divided by 3.802 plus 1 divided by 0.795. This 0.00676 0.000760044. Okay, so this is my relative error. So therefore my absolute error, delta z itself, will be equal to the magnitude of the relative error, which is 0.000760044, times the measured value, which in this case is z, 0.33842. So let's see what we have as delta z. So 0.00 0.0 330.842 times 0.000760 and 44. 0.00025158. So this is my z plus or minus delta z is 0.330842 plus or minus 0.000255158. So this is all about errors, okay, and mixture problems. So I hope you understand, and I hope you've learned a lot from this video. So I'm going to be signing out now, and I am wishing you the best in your exams. And if there is any question in the future, please post it and I'll be glad to solve. Please, those of you that are here for the first time, like and subscribe and give me your questions. I build my content, my video content through your questions. I'll be glad to answer them as much as possible. So till the next time we see, all the best. Solve like Albert Einstein and yeah, be great, be excellent, be precise, and be accurate, because the main aim of studying about errors is so that you can be precise and accurate. Okay guys, take good care.